I'm going to be speaking about some high performance stuff that we've done in Go using sort of assembly and AVX 512 in particular. This is a small sort of agenda. So first, a little introduction. Then I'd like to talk in general sort of about Plan 9 or Golang assembly. Then a little bit about sort of new AVX 512 extensions that are now available. Then I'd like to talk about some projects that we've done with that. So one is basically SHA-256 hashing, acceleration of that, Erasure coding, and I'd like to close with two other projects that are also interesting, I think, in terms of hashing and tool to make it easier to also embed assembly into Go. So a little bit about myself. Most of my career I've been in software development for medical imaging. So that basically means like CT and MRI images, both visualizing those in 2D as well as 3D using GPUs. The last few years I've been active in cloud computing, and I'm now CTO at Minio. And Minio is an S3 compatible object storage server, obviously written in Golang. We have about now 10,000 plus GitHub stars and over 60 million Docker pulls. It's kind of a high performance as well as also allows for sort of high density solutions. So aware of some recent like NVMe developments, those are pretty interesting. So it's developed in Go, available on GitHub under Apache license. And the company was founded by A.B. Parashyami, who maybe some of you know as sort of one of the founders of GlusterFS, which is now part of Red Hat, but obviously was a sort of distributed file system. So let's start with a quick introduction on basically Plan 9 or Golang assembly. So maybe some of you are aware of the fact that Golang actually has kind of a built-in assembler. So as you write normally the regular kind of high level Go code, you can also include assembly. And Go actually has sort of a pseudo assembly language embedded, and this even goes back to sort of the origins and the whole Plan 9 operating system and compiler toolchain. So it is not a sort of direct assembly language like you have for Intel or ARM. So it's generalized. So you have general instructions for like moving, adding, comparing, and stuff like that. And the Go assembler actually obviously translates into the assembly for the specific platform, be it Intel or ARM or ROPC, and then those instructions are obviously translated into opcodes, and that code will obviously run. And most of the time, so there is a translation going from basically Plan 9 assembly to the actual assembly that will run on the architecture that you are running on. And most of the times this kind of translation is logical and makes sense, but there are also some cases where it's a little bit unlogical. So you have to learn that a little bit. It's not completely 100% generic. Because there are architectural differences between the different CPUs. So for instance, on ARM, you have conditional instructions, and you can do that too, but something like that will obviously not work on say, an Intel platform. Also, if you look at sort of the instructions, the flow is from left to right. So if you have an instruction like move R1, R2, it actually means that R2 or the value of R1 is assigned to R2, whereas like an ARM or Intel syntax, it's the other way around. So there's some things you have to get used to, and there's also some sort of pseudo registers that are mapped to different registers on the different architectures. So you have like a frame pointer and a stack pointer, program counter, like that, and the Go assembler has actually gotten quite a bit more complete now, but still you can run into situations where a particular instruction for the underlying architecture sort of is not yet available in sort of the high level Go language. So Go is obviously open source, so you could add it yourself. But Go also has or Go assembly also has the option to basically have sort of the opcodes directly inserted into the assembly file, and that means you can still sort of work around it. And we've written a small tool to help with doing that. If you look at sort of the benefits that you can get from Plan 9 or Golang assembly, is that as long as you adhere to having writing basically pure Go, you still benefit from the very nice and high compilation speed that Go offers. So still the whole Minio source code compiles in seconds, which is really nice. Obviously, if you exploit assembly, you can basically get the maximum performance out of the underlying processor. So if you do that, then you can get significant performance increases over Go code. Some of you may be aware that it is possible to, for instance, use the C-Go tool to include sort of C code into your project. And of course, I mean that's not necessarily that's a good tool, but it does mean that your compile speeds start to suffer, and actually you also have an extra dependency because the C-Go compiler has to be available on the platform that you compile it on, and the C-Go also has some call overhead compared to doing it directly in Golang assembly. Another advantage is that if you use Golang assembly, that if you look at Intel and ARM, they have basically SIMD instructions. And those are basically sort of wide instructions. So they operate on sort of multiple adds or multiplies or what have you in parallel. And this is actually also where AVX 512 comes in nicely, because that is the registers are twice as wide as AVX2, which is twice as wide as AVX or SSE. So taking advantage of those parallel processing capabilities can give quite some performance improvements. And this is one way to do that. As a bit of a warning, if you do this stuff, you will be a little bit kind of on your own, because the documentation is kind of sparse. There's even some documentation going back to Plan 9. Then again, there's source out there that you can take a look at, kind of see how things are done. So also, we have various repositories for Minio where we do this stuff, so you can sort of learn from that. If you want to look at sort of all instructions that are available for a certain platform, you can look at file path is a little bit hidden right now, but if you go into the Go source, there's basically an a_out.go file that basically lists all the instructions that are available for ARM. You can also find it in other architectures that are supported. So later on, I'll show some actual Golang assembly. But I described before that you can come into situations where a certain instruction that you want to use is not available yet, sort of in Plan 9 or Golang assembly. So we've written a small little tool. It's called SM2Plan9S, that basically uses another assembler. So it can either be the GNU assembler or, for instance, YASM, and basically take certain instruction and basically assemble it and extract the opcodes and basically insert those opcodes into the Golang assembly. So this tool works both for Intel and ARM, and we've also added some capability for AVX 12, but I'll speak more to that a little bit later on. But if you look at sort of the upper gray box, there you see basically an AVX instruction, basically doing an add from XMM1 and XMM8 and writing the result in XMM0. And this is an instruction that the Go assembly will not understand itself. And if you run it through SM2Plan9S, then you can capture sort of automatically the the opcodes. So in this case, it's actually 5 bytes. So you can see there's a long and a byte, and the hexadecimals there. That is actually what Go now will basically include in your program to basically run this instruction. You can see that the original instruction is still appended on the same line with basically kind of commented out. So if you, for instance, change your registers and you run SM2 Plan 9S again on the same source file, it will sort of in place update the opcodes. So you can still continue to write in sort of high-level assembly instructions, although in this case it would be the Intel syntax, and then have this tool basically generate sort of the opcodes for you. Yeah, a little bit about sort of AVX 512. So AVX 512 is basically the latest incarnation of basically the SIMD instructions from Intel. They've been around, I think, since like 2014 or 2015, but that was only sort of on the like special Xeon Phi processors. But last year with Skylake, they became generally available. And some of the highlights are that the amount of registers has doubled from 16 to 32. And also the width of the registers has doubled from 256 to 512 bits. And actually this means that if you compute how much kind of register space there is in total, it comes down to 2 kilobytes per core, which is actually quite a bit if you think about it. And again, if you have like a 22 core machine, you have a significant amount of sort of registers. So this stuff is now pretty much generally available with Skylake CPUs. Depending on sort of Skylake CPUs come in different levels like platinum and gold and silver. Generally, it's sort of clocked somewhat lower than AVX2. I'll give an example where actually going from AVX2 to AVX 512 didn't give much speed up, so we had to take a little bit a closer look in order to get more performance out of it. But that's something to sometimes be aware of and measure kind of the results, obviously what you are doing. It also has quite some new instructions. AVX 512 has sort of multiple feature sets. So there is a foundational kind of feature set, and then you have different extensions for different CPUs, and then they enable certain set of instructions that are otherwise not available. What's also nice about AVX 512 is that there is now support for masking. So there's actually there are 8 kind of new K registers where actually K0 is hard coded, so not writable. And you can use these registers to basically mask a destination register. So depending on if you're either operating at, say, byte level or word level or what have you, the bits in these registers can determine which sort of bytes or words are actually written through in the destination register. So it's a nice way to blank out certain results that you don't want to have, and it basically prevents, in certain cases, branching instructions that you would otherwise need to do in order to achieve the same results. So if you look at sort of some of the code there, between sort of the curly braces, you can specify sort of registers, and you can also do kind of operations on those register bits. So you can basically OR in certain masks to either enable certain results to be written through or not be, or basically be masked out. So we've used it actually in some of the stuff that we've done. So that's a nice addition to AVX 512, which wasn't there before, or wasn't available before. Just out of curiosity, we've done some little experiments to kind of see how quick it actually is. And if you look at it, especially if you have, say, a machine with 20 or 30 cores, you can actually get nice performance. So this is actually a small experiment where we've just kind of gotten a feeling for how many multiplies you can do. So it's basically a macro where it does multiplications from basically one source or two sources into a single destination, and then it does that at the word level. So basically you're multiplying 2 bytes and get then a 16-bit results. And if you kind of do the math, then you can see here that if you run it sort of on 24 cores, then you can basically do over 1 tera. Well, it's not flops because it's not floating point operation, but you can essentially do more than 1 tera, 16-bit integer operations per second, which is pretty good. I mean, it's the first time I had this on a computer instead of on a, say a GPU, right? So it's kind of, if you have a machine with a lot of cores and you exploit AVX 5Q, AVX 512, yeah, it packs a serious amount of computing power in it, which is, obviously GPUs are faster still. But if you go a couple of years back, I mean, it's sort of getting in the same range. And then, with all the branching, instructions that, so we've done a couple of things at Minio with Golang assembly and AVX2 and AVX 512. Right now, one thing that we have been working on is accelerating SHA-256. So we already had a repository that used AVX2 and also ARM or the Neon ARM extensions for the ARM processor. But we've added now AVX 512 to this repository too. And we were actually able to get an 8 times improvement over the AVX2 speed measured on a per core basis. So look at the results at the top. Then sort of AVX2 sort of did, say, 450 megabytes per second, and with AVX 512 we got it up to 3.5 gigabyte per second, and this is per core. The original code from this actually was developed by Intel as part of a multi-buffer crypto for IP security. And what it does is it, in essence, processes a total of sort of 16 messages in parallel. So what it does is you literally give it sort of 16 pointers to different message buffers, and it reads in from each of those 16 pointers 64 bytes at one time. It kind of then swaps them around into the 16 ZMM registers, and then goes off and computes it all in parallel. And that's where you get the huge speed up compared to AVX2. There's one caveat that goes along with this, and that is that because obviously SHA results are depending on say a previous block that you processed in the same stream. If you want to do this on a single stream, then you cannot process blocks in parallel. But if you are sort of doing massive compute sort of in parallel or handling a great many clients, then you can pack them up into multiple streams. And actually, I'll talk a little bit about sort of a wrapper that we've written around it in Go, which uses channels to kind of make it easy to work with this. And actually, the original Intel code, used obviously C code and C assembly, used pointers, and they all had to be sort of pointing to similarly sized blocks, but also using the masking support. We were able to use native slices and also slices of different length. Yeah, that's what we've been doing. As I mentioned a minute ago, AVX 512 is still relatively new, so the Go assembler or the Plan 9 assembler does not yet support AVX 512. There's some work ongoing, and maybe by this summer, like a first subset of AVX 512 will be available, so that will be good. But it's also with the masking, it's quite a bit of work that needs to be done to fully support AVX 512. So I think it'll take a couple of releases. So in the meantime, what we decided to do is adapt our SM2 Plan 9 S tool a little bit, in the sense that this code uses basically templates, and so you run the same macro or template with different register configurations. So we really wanted to have the capability to use that feature of the Go assembler. So we kind of used a little bit of trick that normally the Go assembler would error out on sort of lowercase instructions. So we wrote a small patch for the Go sort of assembler to accept basically lowercase non-plan 9 instructions, and then basically run them through our own tool to sort of generate opcodes. And in that way, we were able to add AVX 512 instructions to Golang. You see here, there's actually two links. So in the repository, there are two files. There's an .asm file and a .s file. Now, Go will actually ignore the .sm file and include the .s file, but for now, sort of the master code is in the ASM file. So let me quickly show you a little bit what that looks like. This is the ASM file, and it's kind of a, I talked about the Intel repository where this came from. So if I scroll down, then you will see sort of various macros here. So this is kind of a transpose macro. So you pass in a whole bunch of registers, and it basically flips the bytes around, kind of literally transposes it from sort of vertically to or horizontally to vertically. And this is a pretty large macro. So here basically you see these are AVX 512 instructions with a couple of operands. This is pretty much a one-on-one copy from sort of the original Intel source. And there's also some macros for basically doing the various loops in the SHA-256 calculation, as well as sort of another macro defined to load new messages. And then here actually you see this is actually the assembly definition for the Golang routine. So it loads some parameters off the stack, and sort of initialize the digests. Here it basically loads in. We have 16 input pointers, so we read in those inputs, and here we basically transpose all the inputs that we have written so that we can run them in parallel. And again, if you look at the Intel code, it's pretty much the same paradigm. And then here actually we go into the main loop. And I'm not sure if you ever looked at, say, SHA-256 code, but you sort of have first like 48 rounds of sort of shuffling the bits around and then loading a new message. So you do that for in total like 48 times, and then there are another 16 rounds where you sort of do the same, and finally, if you're done, you've processed basically your last block. There's a last loop where you don't need to load new bytes or blocks to process later on. But again, this was pretty much a one-on-one translation from kind of the Intel code into Plan 9 assembly. And then here we basically computed the checksums, and we write it out and basically exit out. Now, this is not the actual code that is executed sort of by in this case the Intel CPU. So here I have sort of the .s file. So this file is actually read by the Go assembler and basically assembled, of course. So again, here you see the function definition, and here is the Plan 9 assembly, and you will also see here basically the kind of opcodes that originate from the AVX 512 instructions that unfortunately we cannot yet do in Plan 9 assembly. And if you look at the main loop, so this is the main loop, you can see there's quite some assembly there, but these are essentially it's got pretty mechanical in terms of running the macros and then assembling it, and then have the Go compiler take it from there. And as Go gets more support for AVX 5.12, I mean, eventually we should really be able to get rid of the .sm file and sort of move this natively over into the .s file, and then have the Go assembler do all the work. That support is not there yet, so that's why we had to work around it a little bit for now. So that gives you a little bit of a flavor for the code that we are running for this SHA computation on AVX 5.12. What I showed just yet, the .s file, that's the actual assembly code that is executed. And the .s file actually needs to have a sort of sibling .go file, which contains sort of the Go function that you call into, and then that Go function calls the assembly routine essentially. So what we've done is obviously in Go you don't you obviously have pointers too, but then again, in Go you work with slices. So we changed sort of the interface from the original Intel assembly code that used pointers to basically use slices in the Go world. The original Intel code also required all the 16 messages that you were presenting in parallel to be of the same length, and that's of course not really nice. So we extended it a little bit and actually took advantage of the masking support that AVX 5.12 has to, in case a certain sort of message has totally been consumed, then basically you're not reading new information beyond sort of the end of that message block. You're actually still, because you're computing 60 messages in time, you're still, as you run all your calculations, you're still computing something for kind of that digest, but you're simply no longer taking that result with you. So that actually is pretty neat. We were able to keep sort of the interface the same as sort of the normal hash interface. And also we used sort of Golang channels for kind of grouping messages and sort of sending results back. So the link there to the Go code, and obviously that's in the repository as well. Here are some results. So if you, some experiments with like blocks ranging from half a megabyte to basically 10 megabytes. With smaller blocks, you're not getting sort of the full speed up. And again, we're doing 16 messages in parallel here, but sort of from 5 megabytes on, you basically get sort of the maximum throughput. And I think this was on a Skylake CPU with like 3 gigahertz. And also if you, and the upper results they're on a single core. If you run it across multiple cores, so basically that's the second block. So if you double the number of cores, you roughly almost get a doubling of the performance. So from 3.5 to close to 6 gigabyte per second, and then with 4 cores, you somewhere close to 9.5, and with 6 cores, you are at sort of 12.5 gigabyte hashing per second. So so much for sort of the SHA acceleration that we've done with AVX 5.12. Another sort of important part of Minio is Erasure coding. So Minio is an object storage, and we support either multiple disks or multiple servers. And as sort of blobs come into Minio, we will split a blob up into multiple data chunks and compute a number of parity blocks along with those data blocks, and then those data and parity blocks, they get either distributed over multiple disks or over multiple servers. What is nice about erasure coding is that if you lose any number of, say, disks up to the amount of parity blocks that you have computed, you're able to reconstruct the original data. That's pretty important, kind of expensive operation that we need to do because it involves a lot of multiplications. So what we already had in Minio was an AVX2 accelerated version of Reed Solomon that gave good performance, but with AVX 512, we looked if we could improve the performance. Yeah, the first attempt that we did, we weren't really happy with that. So kind of if you go from AVX 2 to AVX 512, one of the simplest things you can do is essentially almost do like a global search and replace in terms of go from YMM registers, which is AVX2 to ZMM registers for AVX 512, and then instead of computing 32 or processing 32 bytes at a time, you're processing 64 bytes at a time. So you basically need half the number of loops to work through a certain message that you need to process. And then you hope that you get a 2x speed up. But in this case, we were not really happy with the results that we were getting. So essentially, we got, say a 1.2, 1.227. That's actually the highest one. Assuming that you're basically doubling the instructions, I mean, you would like to see it much closer to 2x. Although clock frequency for AVX, depending on kind of the CPU model that you have, lower than AVX2. So you're not going to get the full 2x, but at least you should get reasonably close. So this was nice, but not really what we were sort of hoping for. So did some more analysis in terms of how we could get more performance out of it. We kind of felt, we should be getting more out of it. If you actually look at kind of what Erasure coding does, in essence, you split, say, an input message up into a number of blocks, and then you sort of do matrix multiplications in order to compute, a number of Erasure code blocks, and you do that through sort of regular multiplications, but something that's called Galois field arithmetic. But and actually, we were already doing that in AVX2, so that didn't really change. But in essence, you're constantly iterating over input data and computing output data and doing that over and over again. And right now with Minio, we are looking at sort of saturating 100 gigabit networks, and then you want to process, say, 10 gigabyte per second, and that's where you can use some fast code there. The code that we were actually running in AVX2, basically we were computing a single sort of parity message at a time. So in essence, basically a single data row went in, and then we computed an interim result for an output row, and then sort of the second data part came in, and we computed and edited it. That was not sort of the most efficient way of doing that. But once we started to look at if we could do that in a smarter way, and especially what also kind of helped us here a little bit is that the register space going from AVX2 to AVX 512 increased quite a bit. So with an AVX2, you have 16 registers that are 256-bit wide. So you have basically 512 bytes in essence of register space. And with AVX2, not only do you have double the number of registers, but they're also twice as wide. So in essence, your kind of register space is quadrupled from 512 bytes to basically 2 kilobytes. We looked at the algorithm and started working on or investigating if being smarter in terms of computing one row at a time, if we could start to compute more rows sort of in parallel and simultaneously, instead of doing it one at a time and having a lot of memory bandwidth. And that turned out to work quite well. So let me quickly show you a little bit sort of the code that we have. So basically what we're doing is we're using 16 ZMM registers as kind of a cache on the processor. We are computing sort of 4 rows at a time. We are also using sort of 8 input rows at the same time. So here we're basically consuming kind of first message. Here we're consuming a second message, a third, etc. So basically in like a single routine, we can do basically 8 times 4 operations, which in the other way would have meant basically 32 invocations of the AVX2 routine. And that resulted in quite a nice speed up. So if you compare this code to basically the AVX2 that we had, basically we got even a higher than 4 times speed up. So the AVX2 was at, depending on a little bit, sort of the amount of parity that you were computing, say between 750 or 1100 megabytes, and that went to 3.3 or even 4.6 gigabyte per second. So that was a much better improvement compared to obviously kind of our initial attempt. Also, it scales nicely across cores too. Let me quickly show you some other work that we've done. We have also, we're now actually using a new hashing technique, which is called highway hash, which was originally developed by Google Research in C. And we've actually written a Go wrapper for this. Now, this is not a sort of cryptographically secure hash, but for things like fingerprinting, and actually we are using it for bit rot protection. It works quite well. We've optimized this both for Intel and ARM, and in the bottom you sort of see a performance overview comparing the different hashes that we have. And compared to the previous hash that we were using, which was Blake 2B, which gave about close to 1 gigabyte per second, highway hash is more than 10 times faster, actually on a per core basis. So that's if you have a certain use case where you need to do some fingerprinting on blocks of memory, then this may be a nice option. And also, it scales pretty well across cores. So on 16 cores, we were able to do over 80 gigabyte per second. Okay, then these are my last two slides. So what I've been talking about thus far is sort of directly writing Golang assembly. We've also developed a little tool which is called C2Go SM, which, as you may gather, allows you to kind of take C code and sort of wrapping it in Go assembly. So it's a little bit hard to read, but the core idea is, say if you have some C code or some C code, for instance, with intrinsics, if you compile a function and you capture the assembly listing of that compilation, and then you basically lift the body of that function and kind of wrap it in a Golang wrapper, then you can directly invoke that code. So basically on the right hand side of the screen, you see two red boxes, and that contains actually the same assembly, but again in this case the assembly is generated by in this case C-lang. So if you compile some C code using C-lang and get the assembly, and then use C2Go SM, it will basically take the assembly and sort of wrap it with the proper sort of entry for Golang code and the proper exit, and do kind of the hard job of matching up the input parameters and the output results. And if you do this, and an alternative way of doing this is through CGO, so that would allow you to do the same, but then you are incurring a bit of a performance penalty. So it's kind of hard to read, but in this case, doing it this way, I think it's like 20 times quicker or so. So there's the URL there, so you can take a look at that. And then here are some more details, but I'll skip those for now. Here are some resources, some blog posts that we've written on sort of some of the stuff that we have done here.